Hey everyone, welcome back, and today let's solve Leetcode problem 2537 titled Count the Number of Good Subarrays. So we're given an integer array nums and an integer k, and we want to return the number of good subarrays in nums. Now a subarray is good if there are at least k pairs of indices such that I is less than j, and the values at those two indices are equal in that subarray, of course. And they also do kind of define what a subarray is. Basically, it's just a contiguous, non-empty sequence or portion of elements within an array. And when we say within an array, that main array is basically just our entire input array nums. So in example 1, we have our input array nums to be actually just 5 ones, and in this case, k is 10. Now, k equals 10 really signifies that we want at least 10 pairs of indices such that I is less than j, and values of those two indices are equal. And how can we get that? Well, the only possible way to get that is the entire array itself, because technically an input array, or any array in general, is considered to be a subarray of itself. And how would we do that? Well, in this main subarray or input array as a whole itself, we actually do have 10 different pairs of indices, or actually more, I believe, but at least 10 different pairs of indices such that I is less than j, but they're still equal, right? If we take I equals 0 and j equals 1, 0 is less than 1, and the values of those two indices are still equal. 0, index 0 and index 2 would also work, index 0 and 3 would also work, index 0 and 4 would also work, and so on and so forth for all the other indices. And so I believe we actually have more than 10 pairs of indices. In example 2, we have our input array nums to be 3, 1, 4, 3, 2, 2, 4. In this case, k is 2. That means that we want to count the number of subarrays that have two or more pairs of indices that are equal, where one index is less than the other, which really just means two or more equal indices at that point, right? So in this case, there's actually going to be 4 different good subarrays. That's why we have an output of 4. It would be 3, 1, 4, 3, 2, 2. We'd have at least 2 pairs of indices where the values are equal. Same thing applies with 3, 1, 4, 3, 2, 2, 4. 1, 4, 3, 2, 2, 4, and 4, 3, 2, 2, 4. You guys can apply that logic if you will by yourself, but some examples would be this 4 and this 4, and this 2 and this 2. So for the constraints here, we see that the length of our input array nums is going to be between 1 and 10 to the 5th power, and any value, and the k value as well in the input array nums is going to be between 1 and 10 to the 9th power, which brings us to the main observations that we really need to make to solve this problem. Before that, let's go ahead and kind of take a step back and really grasp what this problem really means when they talk about pair of equal elements and kind of the definition of a good subarray, right? Again, let's just take a very simple example. Let's assume we have count of x elements, right? So if we actually do have count of x elements and assume x is just some value in the current subarray, we know that the number of pairs that are formed by them are going to be count at x times count at x minus 1, and that's going to be divided by 2. So to kind of just quickly type them out, the number of pairs formed by them, I'll just say if we have count at x elements in current subarray. And I will comment this out. Give me a minute. Alright. Then what is the kind of formula to get the number of pairs? Well, it would be count at x itself, and that would be multiplied, let me put parentheses here, by count at x subtracted by 1, and this is going to be divided not an integer, just regularly by 2. Right, so why is that? Well, let's go ahead and take an example here to kind of demonstrate that formula. Let's say there's 3 occurrences of x in our current subarray, right? What are the different pairs that we can make using valid different pairs of I and j when they're still equal to make a valid or good subarray? Well, we could take the first index and the second index. We could take the second index and the third index, or we could even take the first index and the third index. These would be 3 different pairs of indices where the values or elements are still equal, making our current subarray good, meaning we have 3 different pairs. Plug 3 into this formula, we'll also get a value of 3, because this would be 3 times 3 minus 1 divided by 2, which is 3 times 2 divided by 2, which is 3 times 1, which is equal to 3. Hence, we have 3 different pairs, or 3 unique pairs of indices that we can form in this good subarray. So what does that really do, and how does that really help us lead to our solution? Well, let me just comment this out real quick. Okay, so the way that would work is as we increase our window size, we know that we're obviously going to potentially form more pairs because we're adding or including more and more elements in our current subarray. So as we increase the window size or add more elements to the current subarray, we have to keep track of them incrementally while we still have k valid pairs, right? Because we don't have to have exactly k pairs. We have to have at least, and while we still have more than or equal to k valid pairs, we know we still have a kind of valid or good window. And what does that remind you of? Well, it's a very classic sliding window algorithm. It's actually very similar to many problems, one of them being, I believe it's Leetcode problem 209 titled minimum subarray sum. It has a very similar logic and solution implementation as this problem, and you guys will see how in just a few minutes. But before that, let's kind of explain our main solution approach to this problem. So, very similarly to Leetcode problem 209, basically, we start with an empty window, right? It's a very standard sliding window technique where we expand the window from left to right using 2 pointers. We're going to have a right pointer, basically our iterator that we go through the entire input array with, and the left pointer is going to kind of be shifted right gradually while we still have valid windows or good subarrays. And we're also going to maintain that frequency map because, of course, we care about the frequencies of elements to make sure that the current subarray is still good, right? To count how many times each number actually appears in our current window to see if it actually forms any valid pairs of indices. And every time we actually include a new number at the right index or increase our current window, we have to then calculate how many new pairs we create using the frequency that we already have being processed and stored in our hash map. Hence the whole point of that dictionary. However, not however, but in the main while loop implementation, while our window still has at least k pairs, we know that all the subarrays that start from left to right in that range of indices, they have to be good. Because if we extend a valid subarray, I would still keep it valid, or even better, add more pairs to make it even more good, if you will. And so that's kind of the main observation of the solution structure to our problem. So let's go ahead and get into the solution here. And like I was just talking about, let's actually initialize our initial hash map here. I'm literally just going to call it frequency. In fact, I'll just call it frequent, or FREQ for short. It's actually not going to be initialized to a regular dictionary, but a default dictionary, and we're going to pass in a data type for the keys, of course, in times of integers, right? Basically, it's going to store the frequency of each element in our current subarray or our current window, and it's going to have all default values of 0, hence the reason default dictionary, and of course, we want default values of 0, which is an integer, and so we're going to pass in an integer data type for every single key to be, right? So now let's actually keep track of the number of total pairs that we've found in our current subarray. Right, of course, going to be initialized to 0. They're going to track the number of pairs or number of equal element pairs, let's say, within our current window, while we still have k or more total pairs. We know we still have a current valid or good subarray or valid window, and so we're still okay to shift our left pointer forward. But more on that later. Now let's actually initialize our left pointer, and of course we're going to be starting at 0. And so left pointer is going to be the pointer that we gradually move to the right to actually kind of minimize our window while we still have a valid window. It's going to be for the sliding window approach, as a right pointer is basically just an iterator that goes through the entire input array in a singular pass. Right, now for the actual kind of result here, what we're going to output, it's going to be, I'm literally just going to call it result. It's going to be storing, of course, the final count of the good subarrays, the number of good subarrays in our input array, which of course should be initialized to 0 before we actually iterate over our input. So let's now use our right pointer and start iterating over the input array as a whole. So for right, where right is again a right pointer that iterates over all the elements by 1 each time, in the range of, very simply, the length of our input array nums, right, because right is going to just keep incrementing. It's basically going to be the current index of our array in each iteration, right? Basically, it's going to expand the end from the right side of our sliding window because we're, of course, checking subarrays that end at each index right as we iterate through the input array. So now let's actually get to the current value in our input array in this current iteration at the current index right. So I'm literally just going to call it value, and it's going to be equal to nums at the current index right. We're basically extracting that from the current index right in the array. It's kind of like the current element that we're iterating over in this iteration. And now we move on to the main step when actually incrementing our window accordingly with this new value. Right, so how are we going to do that? Well, of course, our total pairs will potentially be affected. Right, we have to increment it. Oh my god, I don't know what I did there. We have to increment it, so plus equals frequency at that value. This is the very, very key part of incrementing the number of total pairs that we now have in our current subarray if we actually include the current value at the current index right in our current window, right? Again, basically, we're actually adding or increasing to the number of total pairs that we have for our current window frequency at the current value. Why frequency at the current value? Well, keep in mind, frequency at value basically tells us right now how many occurrences have we previously seen at this moment of the value that we're currently iterating over, right? Basically, before we actually increase the count of the current value in our hash map, we know it already appeared frequency at value times. Of course, the default value for that, if we haven't seen it before, is of course 0. And so we have to basically add one more to form or add this current element to our window. But before that, we know that adding one more would form exactly frequency at value new pairs, because we have that many previous or currently stored value occurrences of that. And so if we add one more, the current value, to the hash map or increment its frequency by 1, we know we're going to have exactly frequency at value new pairs, one different value for the current value. And so the number of different values that we have that can be mapped with it in a pair would be, of course, the number of values that we currently have. And so we have to add that to the number of total pairs that we can now form with our current subarray, because now we're adding this current value to our current window or current subarray. And now we have to actually update the frequency hash map here. Basically, we've seen this value one more time, and so we want to increment its frequency by 1 in this hash map, because of course now it's in the window, it has a frequency 1 greater than it previously did before. Now here's the main kind of while loop implementation, if you will, or rather I should say validation implementation for current window. So while our window is still valid, what's a different way to check that? Well, while the number of total pairs that's actually valid to make our current subarray good, while that's still greater than or equal to k, meaning while our subarray is still good, so that means our current window has at least k pairs. While that's the case, while it's still valid or good, we want to try to shrink it from the left by incrementing our left pointer to the right, while still maintaining this condition to find the minimum subarrays that satisfy the condition to get the total accurate total number of valid or good subarrays in the input array nums. So while this is the case, we'll now actually increment our result. So result plus equals, right, the length of our current input array nums minus right. And this is kind of a simple computation here to actually get the length of our current window, if you will, because once the window from left to right, once it actually has at least k pairs, once it's actually valid, we know that every window that starts from left and ends at any index that's greater than or equal to right, it also has to still be valid, because if we add more elements, it's only going to create more pairs. It's not going to make it non-valid, it just helps us even more. And so we want to add the length of our input array nums minus right to our result, because we know that all the elements that we can add after the index right is still going to help us. And once we do that, now we want to actually move our left pointer forward to kind of keep shrinking our window while this is still the case. So we'll get frequency at nums at left. That's the leftmost value in our current window, and we want to decrement its value by 1. Why are we decrementing its value by 1? Because we're just about to exclude it from our window. We're just about to move our left pointer 1 in this next iteration, or this next line of code here. So once we actually exclude its frequency, or decrease its frequency of the leftmost value, we want to actually remove it by basically shifting our pointer left by 1, or incrementing it by 1. And how do we do that? Well, we literally just take the total pairs and we subtract it by frequency at nums at left. And then we add 1 to left, So left plus equals 1. That's literally the shifting part of this left pointer by adding 1 to it by shrinking the window, and keep checking this continuously by moving this left pointer rightward by 1 while we still have at least k pairs, meaning while our window is still valid. And effectively, once this for loop is done executing, another while loops within them, meaning once we've actually tried every single right index value for all the elements in our input array nums, once we're done iterating through all of them, and once this for loop is actually done executing, once it terminates, we want to return our result, because it would have eventually, once we incremented correctly, stored the number of, or count of good subarrays in our input array as a whole. And so unless I made any syntax errors here, this should be accepted and this should be a valid solution. So let's go ahead and double check that. And as you can see, this really is just about as efficient as you can get it to be. So on a high level, again, what are we really doing here? Kind of just to explain the structure here. Basically, how are we actually counting the number of good subarrays with at least k pairs? That's the main observation. Well, we're using this sliding window approach in the hash map, right? We're expanding the window using our right pointer, iterating over the entire input array, and we're adding the elements into the window and keeping track of how many new pairs are formed and the number of frequency of all elements to actually get that value, and then contracting from left while that condition is still met. While we still have k pairs, we want to keep minimizing our windows to see how many different times we can still have a valid window and keep shifting left to the right. And so we always want to take advantage of the fact that all subarrays ending in right and starting at or after left, they'll still be valid. kind of ate my words there. Basically, all the subarrays that end at right and start at or after left, they're still valid. And so instead of having to actually check all big O of n squared subarrays and checking for all valid or all possible subarrays in the entire input array, kind of like the brute force solution, and checking if they're valid one by one individually, and making a quadratic big O of n squared solution, this is actually much more faster. More specifically, it's big O of n, which brings us to the complexity of this solution. Right, for the runtime complexity, I just said it, it's big O of n, it's linear. Why? Because think about it, it's really just a linear pass iterating through each element exactly once, right? Because we know each element is added and technically also removed from the window at most once in the worst case, and so both pointers would traverse the array once, so it's linear time. It's technically just a single pass. And for the memory or space complexity, it's also linear big O of n. Why? Because in the worst case, we do have this frequency hash map, and it would actually store every single unique element in the array, but that's worst case, and on average, it's really just big O of n or linear memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.